Hi guys, it's Miss Jackson. I just wanted to go over the answers to questions 4, 5, and 6 from yesterday's class. That was to be something you completed on your own. So please have that paper out so you can check what work you were able to finish and jot down any information that you didn't think of when you were solving the problems. The first question that you looked at was number 4, and this goes back to something we've actually discussed as we were learning how to set up our titration and how to prepare our glassware for that titration. Now remember that this base of known concentration that we put into our burette is called a standardized solution because I have determined its concentration using an experimental method. It's been determined in the lab what the concentration is. If I rinse it with water, as we're supposed to do, but I forget to rinse the burette with my titrating solution, that's going to leave water in the glassware, which means when I add the base of known concentration, it actually is going to dilute the solution that's in my burette. And I'm going to think that my base in the burette is stronger than it is. It's actually a little bit less concentrated. When I reach the end point then, down here in my flask, it actually is going to take more base of a diluted concentration to neutralize the acid. So I'm going to think that I have more moles in the flask than I do. And remember, at the equivalence point, the moles of base are going to equal the moles of acid. And if I think I have more moles of base because I think my concentration is stronger than it is, then I'm going to think that I have more moles of acid. And if I think I have more moles of acid, it's going to mean that I believe my acid concentration is stronger than it actually was. So that is the result of having too many droplets of water left in that burette. And that goes back to the reasons that we discussed having the burette prepared properly for your titration. So if you are writing these answers down, this is the answer you're going to want to jot down in your notebook or on your practice page. Yes, having that small amount of water does cause a problem because I believe that my base is actually stronger than it was and that water diluted it just a bit. So pause the video if you need to get this down. Okay. Question number 5 was a titration calculation. It takes 12.5 milliliters of a 0.3 molar hydrochloric acid solution to neutralize 285 milliliters of sodium hydroxide. I want to know the original concentration. Oh dear. I want to know the concentration of the sodium hydroxide solution when I started. So to solve this, we're going to use our equation right here, the moles, the equation I showed you yesterday. Moles of acid times the volume of acid times the number of hydrogen ions is equal to the moles of base times the volume of base times the number of hydroxides. So if I'm going to plug in my information, the molarity of my acid is 0.30. The volume of my acid is 12.5 milliliters, but that needs to be written as liters, so 0.0125. And the number of hydrogens is 1. Okay. That equals the molarity of the base, which is my unknown, my molarity, the volume of the base, which is 285 milliliters, but again, that needs to be written as liters, so 0.285. And then the number of hydroxides on this is also 1. So to solve, I'm going to divide this side by 0.285, and that means that the molarity of my base that you should have calculated is going to be 0.013 molar, and that's your sodium hydroxide. Be sure that you always label your number answers with a unit and a substance. That's proper once you get to the level of chemistry we're at, that every numerical value that is calculated has a unit, and most of the time will also have a substance as well. So hopefully you were able to get this one, because really all you had to do was to utilize this equation that I gave you yesterday in class. It's a really easy equation, and it will work for your polyprotic acids, and it works for your stoichiometry for your 1-to-1 ratios as well. All right, so the last problem had to do with Lulu lab record, and I am pretty sure Lulu's brother Larry was my lab partner in chemistry in college. What you're doing on this one is you actually have 2 test tubes, okay, one with sodium hydroxide and one with hydrochloric acid. So here's my test tube, or my beaker. And what's happening is you've got 2 test tubes that you're putting into the beaker, and they both break open. So down here at the bottom of the beaker, your solution contains the sodium hydroxide and it contains the hydrochloric acid. Okay, so this is kind of what you're working with. So you've got this chemical reaction that's going to happen in the bottom of that beaker. You've added your 2 solutions together. So to solve this, it wasn't outside of your skill set, but it was different than some that we had looked at in class. It made you think a lot harder and work using some background knowledge that you should already have. Let's go ahead and work through this. So I have my sodium hydroxide, and it's going to react with the hydrochloric acid. Because this is a reaction, I need to track my moles. Okay, and I've got 25 milliliters of 0.525 sodium hydroxide, and I broke it into the beaker with 75 milliliters of 0.355 hydrochloric acid. Okay, the question then is, what's the concentration of the solution at the bottom? Is it an acid? Is it a base? What's the pH? So to do that, we need to figure out the stoichiometry of my chemical reaction. So first thing that I have to do to solve this is I have to predict my problems or my products. So we're going to split and switch. So I'm going to break the sodium and hydroxide apart, and I'm going to break the hydrochloric acid ions apart. Remember, they're both strong species, so they separate 100%. My first product is going to be NaCl. And the second product is going to be water. Remember when I've got a +1 and a -1, I have a +1 and a -1, so I get NaCl as one of the products. This one would be HOH. I just went ahead and wrote it as water. So what I need to look at next is what happens in my reaction. What's the stoichiometry that's happening here? So this is where we're going to do a bra chart for these. Okay, we looked at bra charts in the buffer calculations, and when I have a chemical reaction between an acid and a base, I need to figure out the moles of my acid and base, and I need to figure out how much I have left of either one of those, or if they completely neutralized. Because this is going to be a chemical reaction, I have to use the mole amount instead of the molarity amount. So this is where we're going to utilize our formula. Moles or molarity is equal to moles over liters. So I'm going to have to do that for each of my solutions. So for the sodium hydroxide, okay, I know that the molarity is 0.525, and I know that's equal to X number of moles over the volume. I've got 25 milliliters, but I need that in liters, so 0.025. Pardon me, 0.025, so 0.025. That means for my sodium hydroxide, when I do the math, the moles of my sodium hydroxide calculate to be 0.026625, and I'm going to round that up just a little bit. I'm going to round that to 0.0266. So I've got 0.0266 moles of my sodium hydroxide, and I'm going to use the same equation, and I'm going to calculate moles for the acid. Okay? So when I do that, and I calculate the moles of my acid, the moles of my acid calculate to be 0.0131. So when I look at what I have, okay, I don't have sodium chloride and I don't have water. When I look at these two amounts, because it is a 1-to-1 ratio for each of these, and I have different amounts, one of these is going to be my limiting reactant. And in this case, it's going to be my acid. So you should remember from sophomore year that the limiting reactant is completely used up. So I am going to react. Remember, the B stands for moles before, the R stands for moles that react, and the A stands for the moles that we have after. So I react all of my 0.0131 moles of acid, and that uses up 0.0131 moles of the acid. And I will form a small amount, this 0.0131 moles of sodium chloride in water, but we will find out in an upcoming lesson that this particular value for sodium chloride is not going to matter. What I have down here at the bottom is I have no moles of hydrochloric acid remaining, and I have 0.0135 moles of my base remaining. Since I have only base remaining, I know that I have a basic solution. So we can answer this question immediately. Is the solution acidic or basic? In this case, it's going to be basic. So now I have to calculate the concentration. Since sodium chloride or sodium hydroxide is a strong base, all we need to do to find the molarity here for our new solution is to take the moles that we have, divide it by the new volume that we have. So for my new concentration, my molarity of sodium hydroxide is going to be my concentration moles, 135 moles. And I'm going to divide that by my new total solution volume of 100 mils, because I'm going to add 25 milliliters of the base to the 75 milliliters of the acid. That gives me 100 mils, which is a 0.1 volume in liters. When I divide those out, I find that my new solution concentration is going to be 0.135 molar, and that is the sodium hydroxide. So if I want to find the pH of this solution, I have to take this concentration of my sodium hydroxide and I need to find the pH. The easiest way I think to do that is to use the pOH. So I know that the pOH of this solution is going to be the negative log of the hydroxide ion concentration. Because this is a strong base, I know that this dissociates 100%, so I get a concentration of hydroxide of 0.135. So I take the pOH as the negative log of 0.135, which gives me a pOH value of 0.870. 14 minus pOH, or 14 minus the 0.870, gives me a pH value of 13.13. This answer should make sense because I have a base, so my pH should be well above 7, and in this case, indeed it is. Okay. So hopefully this helps. If you have questions, please don't hesitate to reach out and let me know. And I look forward to seeing you on Tuesday. I hope. Talk to you later. Bye.